In the last talk, we have understood the importance of the problem of minimizing or maximizing a black box function, which is expensive to evaluate subject to constraints, by giving a variety of examples in hyperparameter tuning, logic synthesis, MIP tuning, and antibody design. So hopefully that talk convinced you that those type of problems are actually important. What we're going to do in this lecture is we're going to actually continue down that line, but now start looking into the Bayesian optimization method itself, which actually allows us to solve these types of problems. Right. So what we're going to do is we're going to design a data-driven solution. But our data-driven solution has to be sample efficient. So what we're going to do is remember our agent, right? That's the decider that will decide on what value of the variable it will try. Remember, it was, for example, giving us the hyperparameters in the hyperparameter machine learning problem, or it was also giving us the CDR sequence in the antibody design, or the optimal sequence of operators in the logic synthesis, or the value of those parameters theta in the MIP. So that's what I call X in this slide. So that agent will make the decision about the variable X. This variable X will go to the black box function. It will get evaluated, and then we will get back f of x, right? Which the agent will store in its knowledge database. And as time progresses, the agent would have tried different things, like one variable x1 and its corresponding f of x1, another variable x2 and its corresponding f of x2. And we are at the ith round in this example, so we have xi, fxi. So for example, those are like the first value of hyperparameters the agent tried, and the corresponding validation loss. The second value of the hyperparameter and the corresponding validation loss, the ith value and the corresponding validation loss. Or the first sequence of CDRs that has tried and the binding energy value, the second and binding energy value, and so forth. And now over time, what I would like to do is I would like to improve my guesses about X so that I maximize or minimize whatever the problem is, the function, right? So what I would like to do is I want to improve the guess of the optimum, which is X star, and I want to be data efficient. So I don't want this number of trials to be huge. And I would like over time to start improving, right, my guesses of X and the corresponding value f of X. Now, anybody who looks at this problem and is versed in machine learning might say, well, okay, but this is kind of can be framed, right, as an instance of a reinforcement learning solution, okay? That could be true. However, remember that standard reinforcement learning, right, is actually not data efficient. And what we want here is we want to be data efficient. So we cannot just go like PPO on this problem, where we parameterize a policy that will give me, the action will be X, and then the reward will be f of X, and the state is maybe the history. We want to do something a little bit better than that, because the function is very computationally heavy, or it costs us a lot of money to compute or to query at every value X. Now, to solve this or to devise this data efficient solution, we are going to develop the Bayesian optimization solver. So the Bayesian optimization solver is a model-based solver. What it will do is it will try to build a belief over what the black box function looks like, or how would the black box function behave. And based on that belief, right, it will try to find the new point to try to query such that I can improve. So in Bayesian optimization, we have two steps. The first step is to learn a Bayesian model. That's a model of the black box function. So it will tell me how the black box function behaves. And given that model, I will take that into account into the second step, which is what we call an acquisition maximizer. That will tell me what is the new variable x that I would like to try, okay? The Bayesian model is the belief model, right, over the black box function. And not only it gives me a point estimate, so it's not only telling me what the value of the mean is, but it'll also tell me how certain or uncertain I am about my prediction. And given that mean prediction and uncertainty, then I will maximize what I call an acquisition function, which will trade off whether I will trust my model, so exploit it, or I should explore something new, explore a new variable x to get more information. So what I would like you to take from this slide is that Bayesian optimization has two steps. The first step is fitting a Bayesian model. The second step is trading off whether I should trust my model or not using an acquisition maximizer. Now, when we come to building a Bayesian model, we have to remember that we want a model that will give me those uncertainties, right? But it has to be data efficient. Because remember, I cannot just throw a fully flushed, let's say, ensemble of neural networks here and all are deep neural networks, because I don't have so much data, right? I want to have a data efficient model. Why data efficient? Because remember, my black box is expensive to query, meaning that I cannot try so many variables x, right? So what I would like to be able to do is I would like to fit a belief model over my black box function, and I would like that to be data efficient. Now, to do that, we're going to use something called Gaussian processes. I will describe a bit what Gaussian processes are, but they are data efficient uncertainty quantifiers. That's how I like to see them. Now, this is the book about Gaussian processes, which is called Gaussian Processes for Machine Learning. It's by Professor Carl Rasmussen and Professor Christopher Williams. So I have the book here, and I think you should really read it. This is like the Bible, right, for Gaussian processes that everybody interested in uncertainty quantification goes to and reads. So definitely, I think it's worth a read if you're interested at all in this topic, or if you're interested in probabilistic machine learning in general. So the first thing we're going to do now is we're going to dig into each of these two steps, i.e. building the Bayesian model and maximizing the acquisition. And then we will give you a library, which is actually kind of doing these two things for you, so you don't have to worry much about all the mathematical details involved. Right. So here I will be using material that are borrowed from amazing professors that were kind enough to either open source their stuff on YouTube, which I borrowed from, or they were kind enough to allow me to use their concepts or their ideas and their slides. So those are, some of this material is borrowed from Professor James Hensman, Professor Richard Turner, Professor Nando De Freitas, and Professor Niels Lawrence, of course, in addition to the Bible itself that I will be using. Right. So in order to understand what a Gaussian process is, right, we're going to step back and talk about a univariate Gaussian distribution. So we're going to build it step by step. We're going to go univariate Gaussian distribution, then a multivariate Gaussian distribution, then a Gaussian process. Now, by no means, this is the best introduction or the only introduction to Gaussian processes. This is an introduction that is a working introduction for Bayesian optimization. I'm not really, the goal here, right, is not to really get you experts in Gaussian processes, but rather to give you the idea on how you train and use Gaussian processes inside Bayesian optimization. So we're going to start with the simple univariate Gaussian distribution, which I hope a lot of you are familiar with. But if you're not, don't worry. Here's how it goes. So I'm sure you've seen this bell curve before, right? So this bell curve is a univariate Gaussian distribution. The univariate Gaussian distribution has two variables that dictate how it looks. The first one is the center, right? So that's where is this bell curve centered? And the second one is the variance. How wide is this bell curve? So here I show you a couple of different bell curves, like the green one, the blue one, the orange one, the red one. They are centered at different locations, and they have different variances. The smaller the variance, the more peaked the bell curve looks. The larger the variance, the less peaked it looks. So, for example, this has a smaller variance than this guy. And where it's positioned on this axis is given by the center, which we call the mean value. So the equation of a Gaussian distribution looks something like this. So you have 1 over sigma square root of 2 pi e to the power of minus 1 over 2 sigma squared x minus mu squared. Now, this is the variance sigma, right? It dictates how wide things are. And this is the mean mu. It dictates where the thing is centered. So x minus mu squared is telling me how far my variable x is from the mean, and sigma squared is telling me, how, kind of wide this Gaussian distribution is. And we can do a lot of cool things with this Gaussian distribution. Maybe a lot of literature has been built on this. But now all I want you to take from here is that, okay, this is a distribution which has a mean and it has a variance. Both of those are numbers because my variable x is one dimension. So to specify how this Gaussian distribution looks, I only need a position where my Gaussian is centered on the real line. So that's one value. And I also need one variable to tell me how the variation is happening, and that's sigma. Right? So each of those is a constant. But now we can go from this and generalize to a multivariate Gaussian distribution. So what if my x was not a one-dimensional vector, right? What if my variable x that I'm interested to define a distribution over was a vector? So it was in 2D space, 3D space, and D space. So remember here, right? When I defined my variable x, my x was a 1D variable, right? But now, if I want to deal with a set of higher dimension variables, right, then I need to be able to define it in more than just one dimension. So that's why I will be dealing with a vector x. So that x will have multiple components. So it'll have x1, right? x2, this is the first entry, the first dimension, the second dimension, the third dimension, right? Up to the dth dimension. So if I have d-dimensional vector x. So now notice, right, that we are working in this space where we have d-dimensional vector and not a one-dimensional variable. Okay. In the one-dimensional case, we needed two things, right, to dictate how that bell curve, how that Gaussian distribution looked like. We needed a mean variable and a variance variable. Right. But now if we are working in a multidimensional case, right, I don't need a mean variable anymore. Because to specify the center in that d-dimensional space, I actually need a d-dimensional vector. I need to have a d-dimensional vector to tell me, right, where this bell curve is actually located. And not only that, if I want to understand the variation of this bell curve, right, then I need to be able to understand the variation across these different dimensions, right? So I want to see how I vary in this, how I vary in that, but also how I cross vary between them, right? So instead of having a mean value and a variance value, I will have a mean vector, which I call mu, right? And I have a covariance matrix, which I call sigma. Okay? So let's look into the changes between the 1D and the multi-D, right? So if we look into the changes between the 1D and the multi-D, instead of having a mean value, now I have a mean vector because I need to specify the center, in a d-dimensional space. And instead of having one variance that tells me how I vary, now I have a matrix that tells me how I vary across those dimensions. So I need to understand how I vary in this dimension, and cross between these dimensions. Right. So those are the main changes. Now, if you look at this equation, you will freak out like, okay, what is this equation doing, right? Okay. But let's dissect it a little bit to better understand what's really going on here. Okay. Now, let's look at what's inside the exponent, right? So let's look into this x minus mu transpose, sigma inverse x minus mu. And for now, right, let's imagine that this is identity. So we're not really caring, right, for the cross variation between them. And we just say, okay, sigma is identity. I just made that assumption for now. So now if I look at the assumption that I made, I will have something that looks like this. So x minus mu transpose, right? Identity, which goes away because it's just identity. X minus mu. So that's what I will have inside the exponent, right? So I will have x minus mu transpose x minus mu because I assumed my sigma was identity. Okay. Now, let's look into this x minus mu transpose x minus mu. And just let's abstract a little bit. Let's forget, what is x minus, that it's x minus mu. Let's call this vector A, right? So what I have here, right, is a vector that looks like A transposed times A, where I called A x minus mu, right? So this is a vector, right, which is A transpose. So it's made of A1 up to AD, right? So if I'm working in D dimensions, and that's a row vector because it's transposed, multiplied by a column vector, which is A1 to AD, right? Okay, good. So what I've done so far is I assumed this is identity. I took x minus mu transposed x minus mu. I'm trying to understand what that is. I defined A to be x minus mu, just to simplify notation. And now I'm looking at A transpose A, which is where A is x minus mu, so it's just the same thing, really. Now what you can see from this, right, is that this will be a 1 by d vector multiplied by a d by 1 vector, right? And now that is a 1 by 1 result, meaning it's a number, right? So it's a 1 by d by a d by 1. So it's a 1 by 1, it's a value. Now, what is that value made of? Well, that value, how would we compute this, right? We take this, multiply by that, take the second, multiply by the second, and add them, third by the third, and add it, fourth by the fourth, and d by the d, and add them. So you get a1 squared plus a2 squared, plus dot, 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 up to a d squared, right? So, when you multiply those together, you will get this. But what is this? So what is the first component squared plus the second component squared plus the third component squared plus the dth component squared of a vector? Well, that is nothing but the norm of the vector squared, right? So that's nothing but the norm of the vector A squared, right? So when we did A transpose A, we just get the norm squared. And now remember that A is x minus mu, So what you really got is the norm of x minus mu squared, right? That's what we got. So when we assumed this is identity here, right? And we worked through x minus mu transposed x minus mu. We called it A. We computed this. We got the norm of x minus u squared. But now that is interesting, because if you actually go back and look at what was happening inside this equation, you will notice that the exponent, right, of the inside the x, this was distance between x minus mu squared. So really what is happening here is that this exponent in high D is nothing but measuring a sort of a high dimensional distance, between your variable x and your mu variable. So now what we could see is that the exponent part, right, if we assume that the sigma is identity, if we assume this is identity, right, it will be nothing but the norm of that vector squared, which is really analogous. I mean, intuitively, it is analogous to the one-dimensional case where you have x minus mu squared. So both in the exponent in high D or in 1D, they are just measuring the distance, how far you are from your center, where the center in 1D was a variable, in high D it's a vector. Okay. Now, we assumed that the sigma is identity, but in reality, it might not be identity. So if it's not identity, right, what will happen when you work out through the math? You will get a weighted norm. So you will get a norm that is weighted by this matrix sigma inverse. I mean, we typically write it like x minus mu sigma inverse squared, right? So what we're really getting is we're getting a norm that is weighted by this matrix sigma. And this matrix weighting, all it will do is it will squash the norm or extend it in different directions. But again, if we look at this and we go back to the 1D case, right, we also notice that this is a weighted distance by the 1/2 sigma squared, which is like a sigma inverse, right? So in reality, also, this one dimension is the norm, or the distance in one dimension is being weighted by, the sigma squared. In high D, we also observe the same. So in reality, what is going on in high D is nothing but the low D thing, right? Not just written in high D mathematics, really. So it is a weighted distance, right, inside the exponent, and the mean is a vector and the sigma is a matrix. And there is a normalizing term, which makes sure that this integrates to 1, similar to the normalizing term we had in the 1D case, which was 1/sigma square root of 2 pi. So this high D Gaussian description is really intuitively, right, is an analogous thing to the low D Gaussian, but in higher dimensions. And here I draw for you like different, 2D Gaussian distributions, where one is centered at 0 and has a covariance matrix 10, 10, 0, 0. And so now what you see, in case you change the sigma to 10, 10, 5, 5, things get a bit more squashed because you have more variation in one dimension as opposed to not having any variation across these dimensions. Right. Now, as you see, this equation, while we understand it, right, it's actually tedious to write. So instead of writing it every time as 1/2 pi d over 2, etc., I'm just going to create this notation where I'll use a mathcal n, mean mu, vector, sigma matrix. When I write this n, mean mu, vector, sigma matrix, I literally mean this equation. So just not to write it, I just created a simplified notation, right, which looks something like this: mean mu and a sigma matrix and this mathcal n. Okay. So now we know how we can go from a 1D, right, to a high D Gaussian distribution. Now, why is that interesting, right? So what is the point of all this? Why is that interesting? Well, there are very nice properties that we can borrow if we have this high D Gaussian distribution, right? Because the first thing we could do is we can do something called marginalization and something called conditioning. And both those steps are tractable because we have a multivariate Gaussian distribution. So let me go slowly across this, what we actually mean by that. So let's imagine we have a vector x, which is made of two vectors. We call them x1 and x2. So what I really did here is I took a vector x, which is made of x1, x2, x3, up to xd, right? So I took, this vector, and then I just actually collected those components together and called them x1, and collected the remaining components together and called them x2. So really, I've done nothing fancy. I just, for ease of notation, I rewrote, this p over x, which is this multivariate Gaussian, into, a form over these two vectors, x1 and x2. And now, remember that there's a mean vector and there's a covariance matrix. So now the mean vector is actually the mean vector over the first components, which I call mu1, right? And corresponding to x1. Sorry, and a mean vector across mu2, which is corresponding to x2. And I also split the covariance matrix into a cross covariance between the two, sigma 1, 2 and sigma 1, 2 transpose, and one across only the components of x1 and the components of x2, right? So now all I've done really is I just took this equation I wrote before and just arranged things to look in a nicer way, where I said, okay, the first component's x1, the second component's x2. Consequently, I will take the first chunk call it the mean mu1, the second chunk, call it the mean mu2, and then, the covariances as well, split them as x1, like covariance over one, covariance over second, and cross covariance between them. So now imagine I have these two vectors, x1 and x2, jointly distributed according to a multivariate Gaussian distribution. So what does that mean? It means that the joint distribution P of x1 and x2, right? I wrote it a comma here. So the P of x1 and x2 is jointly distributed according to a multivariate Gaussian that looks like this. So imagine, I give you that. And then I tell you, okay, knowing that the joint P of x1 and x2 are distributed according to this multivariate Gaussian, right? What is the marginal over x1, P of x1? So in order to get the marginal, you just need to integrate out the other variable you're not interested in, right? So if I want to get P of x1, all I need to do is compute the integral of P of x1 and x2 with respect to x2. So when I marginalize, I can get rid of this guy, right? So I can get rid of this second variable I'm not interested in. So when you work out the math, it turns out that it is super cool that the marginal of a multivariate Gaussian is a multivariate Gaussian itself, with the corresponding chunk of the mean and the corresponding covariance matrix. So the idea is that we started from P of x1 and x2 being a jointly Gaussian distributed. And now when I asked you, what is P of x1? Can I marginalize out x2? You did the integral, right? And you were able to show that P of x1 itself is a Gaussian, right? And you only need the chunk of the mean that is responsible for that variable x1 and the chunk of the covariance matrix that is responsible for the variation in x1. So this is a very nice property, because now if I have a variable that's jointly distributed according to a Gaussian, a multivariate Gaussian, and then I ask you, what about the remaining chunk of that variable? It turns out it's also a multivariate Gaussian, which is like super awesome. The second thing we might be interested in is conditioning, right? So it's like, I would like to condition one part of the vector on another part of the vector. So again, imagine that P of x1 and x2 are jointly Gaussian, multivariate Gaussian. Now, I might be interested in asking the question, given I've seen some parts of these observations, given I've seen x2, for example, I know those values. What about x1? What's the distribution of x1? So if I know x2, right, I can ask the question, what is P of x1? Again, it turns out the beautiful property of multivariate Gaussian, it's also Gaussian, but it has a bit more complex mean and covariance. Okay? So keep those in mind. As an exercise, try to derive them if you want. And if you have questions, write me in the comments. I'll be happy to help you derive those. But the idea now is that if you have a multivariate Gaussian, you can marginalize it out with respect to certain variables and get a multivariate Gaussian. You can condition on some variables and still get a multivariate Gaussian. Okay, good. Right, we are happy with that. So we hopefully understand that. And if you have any questions, again, please write in the comments. But now, okay, why is this all important? Why was I, even talking about this? So now let's go back a bit to machine learning, right? Imagine now, right, I collected a data set. So imagine now I actually collected, a data set made of x1 fx1, x2 fx2, x3 fx3, and so on, right? So imagine for now I collected this data set. So for example, I was running my BO algorithm, and then my BO algorithm tried a set of hyperparameters and got back the value of the validation loss. So I call that x1 fx1. Then tried another value of hyperparameters and get x2 fx2. And try the third value of hyperparameters, get x3 and fx3. All right, so we have this data given. Okay, now let's make an assumption. Let's assume, right, and maybe some would argue this is a big assumption, but for now, let us assume, right, that the distribution of the f of x values conditioned on the x values is actually a multivariate Gaussian. So I'm making the assumption, right, that my validation loss value conditioned on the hyperparameter jointly, of course, is a multivariate Gaussian. Okay? So that's an assumption I'm making. We don't like it, maybe we don't, right? But for now, let's make that assumption. So what I'm really saying is I'm saying, okay, the value of my f of x over the 0.1, the 0.2, the 0.3, so over the validation loss on hyperparameter 1, the validation loss on hyperparameter 2, the validation loss on hyperparameter 3, or, for example, the binding energy on CDR trial 1, binding energy on CDR trial 2, binding energy on CDR trial 3, conditioned on the hyperparameter value 1 we tried, the hyperparameter value 2 we tried, the hyperparameter value 3 we tried. We're going to assume that's a multivariate Gaussian. So we're going to say, remember this N notation I introduced. We're going to say it has a mean vector which is centered around 0, right? And it has a covariance matrix. Remember, now we will have a 3-dimensional problem because we have 3 points, right? And that would be a covariance matrix which will be 3 by 3 dimensions, okay? So all I've done, right, is that I made the assumption, okay, that my outputs, black box function value, evaluation, validation loss of a hyperparameter, binding energy of CDR, conditioned on the value of the hyperparameters, is multivariate Gaussian distributed with a 0 mean, right, and a covariance matrix K. Okay. To define this covariance matrix K, the covariance matrix is reflective of what, right? The covariance matrix is reflective of how this f of x is varying, really, right? So how the f between 2 points varies is kind of the entry of a covariance matrix. So it tells me, how the first y or the first f of x with respect to the second f of x will vary. Okay? So in other words, this covariance matrix is going to tell me how the change is going to happen in f. Okay. Right. We're going to make an assumption here, another assumption. We're going to say that the covariance is going to be a function of the input. We're going to say that the way the function varies, f at one point versus f at another point, we're going to say the way this function varies, right? This is going to be a function of the inputs themselves. So if I have an input x1 and an input x2, and I have f of x1, f of x2, I'm going to make the assumption that the way the f of x1 and f of x2 are going to change is a function of the variables x1 and x2 themselves. And this kind of makes sense. It's kind of intuitive, right? And this is going to be called the kernel, right? So here I give you an example of the kernel where I will tell you that the way f of xi and f of xj vary is a function k of xi and xj. And now, intuitively, right, we would like, if the points are close to each other, we would like their f values to be close, or the covariance of the f values very highly correlated. And as we go farther away, right, then we would like this correlation to decrease. So for example, what I would like to see is that if I'm very close to x1, I would like those variations to be highly correlated. And maybe the farther I go, right, I would like those variations to reduce. So this is one form of kernel, which is called this exponential kernel, X kernel, or RBF kernel. And it's really just defined as a function of the distance between xi and xj. So if xi is very far from xj, then this x of e to the minus infinity, if they are very, very far, let's say, so their limit will be 0, meaning that if they are very far, there's not much correlation between the function values here and there. If they are very, very close, then there's a high correlation, between these two variables, between these two function values. Okay. So this kernel, right, is actually measuring the covariance, okay, between the function values as a function of the input distance between x1 and x2. In this example, the closer, the x's are, the more correlated their function values are. The farther, the x's are, the less correlation their function values have. Now, by no means, this is the only kernel. You can come up with fancier kernels. However, remember, kernels have to abide by certain properties because we need to be able to invert sigma. We need sigma inverse, right, in our equation, if you remember. And if you look into this amazing book again, I think they have a nice chapter on this. I think it's chapter 4, right? So chapter 4 talks about covariance functions, different covariance functions you can come up with, and their properties. I mean, this is really well explained in this book. So if you're interested in digging deeper, please buy this book, have a read through chapter 4. Okay. Now that we defined this, I think we can go a bit broader and actually look into more what a Gaussian process is. Okay. Now, before I do that, however, right, there's one thing I would like to mention. Why is this entity, right, that I described to you, is something important, Why is this entity useful, yeah? Like, what's the point of this, Okay, one point of this is that now I can give you a new data point x, and I tell you this new data point x, let's call it x star, is also jointly Gaussian distributed. And then I can ask you, can you give me the f of x value for that new value x star? So in other words, imagine now I give you a new x star value, right? So I tell you, okay, what do you think will happen for the function value f of x star? Yeah, if it is also jointly distributed as a Gaussian, according to our previous model. So in other words, imagine I tell you you have a new variable x star, and I want you to tell me what happens of f of x star if it is also jointly Gaussian distributed with respect to the others. So in other words, what is this trying to say? This is trying to say that now I can ask you to make a prediction about the new value x star if I assume it's also, right, jointly Gaussian predicted. Well, how would I do that? So if I give you this new x star, all you need to do is you need to compute its corresponding row and column in this covariance matrix, right? And now once you do that, now all you need to do is actually you need to do a prediction. And in order to do a prediction, you can just condition. So in order to know what f of x star is conditioned on x1, x2, x3, x star, and fx1, fx2, fx3, all I need to do is just use the condition formula that I told you about before in order to have a prediction, right, about that value. So what is so cool here is that now, if I'm assuming many things are jointly distributed as Gaussian, right? And now I tell you, okay, this is in the new x star. What is f of x star conditioned on those? All you need to do is just use the conditional formula. And not only you get a point prediction, but you get a whole distribution prediction. So you get a distributional posterior prediction, right? So in other words, if now I give you the x star and I tell you, condition on x1, x2, x3, x star, fx1, fx2, fx3, what is the value of fx star? Now you can derive the Gaussian distribution, which has a mean mu star and a sigma star. Okay. So in other words, now we are actually can make a prediction. And that prediction not only is a point estimator, but it's also a Gaussian. So it means it's a distribution, which has a certain mean and a certain variance. How do you get these means and variances? Well, the way you get them is by using my conditional formula. So if you apply it, you will get the mean to look like k of x star x, k inverse f, and the sigma to look something like this. So what is really happening is that when you are making a prediction mu star, you're doing a linear combination of the kernel basis functions, and that's how you are making the prediction of where the mean of that f of x star would look. Right. So we described a lot the multivariate Gaussians, and we went through their prediction capabilities and so on. I mean, for practitioners, maybe you don't really need to worry much about the math because there will be libraries that you can just use in order to make these predictions, right? But now with this, we can actually define what a Gaussian process is. So a Gaussian process is a collection of random variables. So we have many random variables. If you take any finite number of those random variables, you will get a multivariate Gaussian distribution. So no need to worry much about this. All I want us to understand is if I tell you that something is distributed according to a Gaussian process, so if I tell you that there's something like f of x distributed according to a GP with a mean m of x and a kernel function k of x, x prime, then what I want you to understand is that using this definition, right? Using this definition, any finite number of those variables will have a multivariate Gaussian distribution, meaning that if I know that f of x is sampled according to Gaussian process, then if I give you a set of data points x1, fx1, x2, fx2, and so on, then those are multivariate Gaussian distributed with a mean vector mx1, mxn, and a covariance matrix kx1 up to kx1xn and kxnxn. Okay, so all I'm saying, yeah, is what we need to know for this lecture is that if I tell you something is distributed according to a Gaussian process, that means over a finite set of observations, f of x will be distributed according to a multivariate Gaussian distribution, which is what I wrote here, and it has the mean evaluated at these endpoints that we've observed, and the covariance kernel on this n by n. Okay. Now, what is learning in a Gaussian process, right? When it comes to Gaussian processes, what we're typically going to do is we're going to assume the mean has a zero mean, and that's okay because we can normalize, the data to have zero mean. But in terms of the kernel, we are going to leave a set of free parameters for this kernel, which we call in this example sigma and lambda. And those free parameters, right, are going to dictate different types of functions that this Gaussian process can fit. And now I'm going to be looking for the best set of hyperparameters, right, sigma squared and lambda in this case, that will fit my data well. Okay? So I'm going to start by assuming that I have some form of a Gaussian process. And then what I'm going to do next is I'm going to now fit the parameters of this Gaussian process, which is theta here, right, in order to maximize the performance or maximize the accuracy on my data. Now, Bayesian people would like to think that we really don't need to fit this. We can integrate out those parameters. We're not going to go into that yet. We're just going to talk about marginal maximization. Right. So to recap, I'm trying to tell you here that if I tell you that something, a function f, is distributed according to a GP, that means over a finite number of data points, x1 to xn, it will be distributed according to a multivariate Gaussian distribution. And I'm going to say that the kernel, I don't know how to pick the kernel, so I will just define a kernel class of functions and have sigma squared and lambda d are parameters in this example, which I don't know. And then I'm going to fit them so that I do well on my dataset. So in order to fit those, we're going to use this type 2 marginal likelihood. But the idea is we start from the following assumptions. We might not like those assumptions, and there are remedies for them in the awesome book and also in the awesome literature. The first thing we're going to do is we're going to assume that we have a Gaussian noise likelihood. So we're going to assume that the y values we observe are the function value f of x plus some epsilon, where the epsilon itself is a Gaussian noise. And we're going to assume that the function f of x is a Gaussian distribution, is a Gaussian process prior, coming from a Gaussian process. So in other words, right, what I'm saying is that my function, let's say this is my function and those are the y data points I've seen, right? Like this is the y data points that I have seen. I'm assuming that my y value that I see, right, is centered on this function f of x, and it has some Gaussian noise epsilon around it, where the mean, the mean should be, oh my God. So the mean should be somewhere here, and then there's some noise epsilon that will give me this point x, this point y. So therefore, I have a Gaussian likelihood assumption of noise. And I'm also assuming that my function f itself is actually distributed according to a Gaussian process. Remember, when I say the function is distributed according to a Gaussian process, right, then if I give you n data points, that means I just get a multivariate Gaussian distribution, right? So if I'm interested to understand what is p of, f vector given a set of data points x, right? So f vector is just f1, the evaluation on the first, up to the evaluation on the nth data point, right? So it's f of x1, f of x2, up to f of xn. Then this will be nothing but a multivariate Gaussian distribution with mean, which we assume to be 0, and a covariance kernel, which has those parameters theta, which we didn't see, or we were going to fit. Right. So, so those are my assumptions, right? So I'm assuming that I have a Gaussian noise likelihood, and I'm assuming that my function f is actually coming from a Gaussian process. Right. Now, given some data, remember, if given some data, then this will not be GP anymore, it will be a multivariate Gaussian, right? We just talked about it in this slide. We said that if f is sampled from a Gaussian process, then on a finite data point, it will be a multivariate Gaussian distribution. Okay. And now, in order to assess how good my fit is, or how good my parameters of my kernel are, I'm going to use the marginal likelihood. So I'm going to be interested in what is P of y given x. So what is P of my observations of the black box function in my case, conditioned on my input x, right? So what is my P of y conditioned on x? Now, using the marginalization property, I can rewrite this as P of y and f given x df. So imagine I marginalize out these values f, this vectored values f over the x's I have. Then I will get P of y given x. Then I just apply the chain rule of probability. So then I can write this to be P of y given f and x, P of f given x df. So how did I go from here to here? All I have done is this is a P of A and B conditioned on something. Then I just factorized it. Remember, this comes from the prior, and this comes from the likelihood. So how likely is my y conditioned on my f and my input x? And this, what about the values of f conditioned on my input x? Remember, we know this, and we know this because we have this assumption. But this P of f given x, we know it from the previous slide, because if f is sampled according to a GP, then on a finite number of data points, this becomes a multivariate Gaussian distribution with the mean mu mx1 up to mxn, and the covariance kernel k x1, x1, and so on, and this big matrix. Right. So that's what I'm using in order, to fit my GP. And now, as we said, this P of f given x is nothing but the kernel, which has those nothing but the multivariate Gaussian, which has those parameters theta. And remember, we had a 0 mean assumption. And this is nothing but a multivariate Gaussian distribution because the likelihood is Gaussian. Anyways, once you work throughout this integral, then you will get an equation that looks like this. And what we do in Gaussian processes, right, is that we will do like an optimizer with respect to theta to maximize this log P of y given x. This will have two terms, like a data fit and a model complexity fit. And we are not like extremely, we're not going to bother ourselves by how we got here. If you're interested, please work through this integral. And because of the nice properties of Gaussian, product of Gaussians is a Gaussian, integral of Gaussian is a normalizing term of another Gaussian, you will get this type of equation. And now, in order to fit the Gaussian process, all we're going to do is we're going to take gradients with respect to theta of this equation, or use second order optimizer, or use Adam, or use whatever you. Right. Now, at this stage, you are worried. There's a lot of math. Oh my God, and so on. Right. But you really don't need to worry much about all these things I described. If you're just interested in using, Gaussian processes and BO, there are well-established libraries, that will allow you to kind of do these fits without really needing to dig into all the math details. One of the most amazing libraries is GPFlow, and another one is GPyTorch. So what you need to do in GPFlow is you would need to define what kernel you are using. Remember, we assume this RBF kernel, but there are different types of kernels, again, in the book. And then you would like to dictate what type of problem you are solving. So for example, this is a Gaussian process regression problem because my Y value are continuous, for example. And you would like to say which optimizer you want to use in order to maximize your marginal. And then all you're going to do is just op.minimize with respect to a training loss, and then this will fit the Gaussian process for you. So that's the training step. Oops, that's the training step for your Gaussian process. When you finish training and you want to do a prediction, remember this conditioning I mentioned. Again, you don't really need to worry much about all these equations. In GP flow, all you need to do is like m.predict on some input points, and that would give you like the prediction mean and the prediction variance, mean and var. Remember, we predict the distribution. This is very similar to GPyTorch as well, another library that you should consider using for Gaussian processes, where here you define the kernel, you define the likelihood. Remember, we said we had a Gaussian likelihood, but you can use other forms of likelihood. You define what type of GP model you want to use, because if you change the type of likelihood, you don't have tractability anymore, so you have variational approaches. Or if you have a lot of data, you also have variational approaches. And then you decide, okay, what optimizer you want, like this is torch.op.adam. And then all you're going to do is just like fit it, right? So you'll just have the loss, which is the marginal likelihood we just derived. Then you would do loss.backward and optimizer.step. Once you're done, you can also do a prediction. All you need to do is just follow these simple lines of code. Of course, there's a very nice documentation on both of those that you could use. But again, GPyTorch will give you this prediction of the mean and also the variance. So here's an example that I give you that you can fit a Gaussian process nicely, using by just like a few lines of code. So what you see here is that before observing any data points, the Gaussian process prior was all over the place. Upon observing data points, now you reduce the variance around those and you have a better fit. And as you see, to fit everything I described, it's not much work. It's just a couple of lines of code where you define the kernel and you also define what type of optimizer you would like to use, and then you just minimize. And now when you want to do predictions, again, it's like what I showed you before, but all you need to do is predict f.samples, and then from that you are able to predict, and then you can get these nice plots. Right. So, okay, so we finished the first step of a Gaussian process and what it is. And now we can talk about the second step of the BO, which is the acquisition function step. So if we recap, right, remember that our Bayesian optimization solver, right, worked in two steps. The first step was to learn a Bayesian model, and the second step was to maximize an acquisition. And then what it does is that it tries, after maximizing the acquisition, this value, and then it repeats. So now what we really need to do is we need to talk about this second step. What is an acquisition and how do we maximize it? In terms of acquisition functions, there are two generic types of acquisition functions. One is called myopic acquisitions, another is called non-myopic acquisitions. In terms of the myopic acquisitions, we have four maybe widely used and widely known approaches. One is called expected improvement, the other is called probability of improvement, one is called simple regret, and the other is called upper confidence value. On the non-myopic side, we have many cool things like knowledge gradient, entropy search, and so on. However, from my experience, those have not been very scalable yet, so we're going to focus more on the myopic acquisitions. So to start, let's start with the first acquisition, this expected improvement. Okay. Now, what is an acquisition doing? Like, let's think about that for a second. So given this Gaussian process, right? So given, the Gaussian process and its uncertainty estimates, right? This acquisition step should decide, okay, what should I pick next? Given that that's what my function looks like, that's the belief of my function, Okay, cool. That's the belief of my function. All right. Okay. What should I pick next? What should I try next? Well, if we think about it, there are two things we need to trade off here. We need to trade off, the uncertainty, the uncertainty from my model, right? that we fit, like how certain it is about certain areas of the space. And also we need to trade off, whether I should, go with this uncertainty or I should focus more on the mean, right? So should I exploit or should I explore? Now, to formalize those notions, people came up with these acquisition functions. So one of them is the expected improvement, and the others I will show you later. What expected improvement does is it will measure, right, how likely we are on average to get a better point than what we have seen so far. So we take what we've tried so far, we take the best value f, that we've seen so far, and then the expected improvement, what it's going to do is it's going to try to find a point which is better on average than what I have seen so far. But now when we say on average, we mean expectation, right? This expectation has to happen with respect to some distribution, okay? So I want to do well on average, but then I want to do well on average. This expectation needs a distribution. So what distribution should it be? Well, it could be my belief over what the black box function does, right? So it could be the Gaussian process I fit, because the Gaussian process gives me the belief of what the black box function will do. Given that belief, now I can ask the question under that belief, which input point x will give me better value on average than everything I've seen so far, or than the best thing I've seen so far. And this is what this equation is actually depicting. If you look into the inside of the max, right, it is saying it's the value of f of x minus the best I've seen so far, right? So that's this minus the best thing I've seen so far, right? And of course, that's maxed with 0 because I don't want to say negative things. Okay? And this is averaged over the posterior of the Gaussian process. So this part here, this chunk here, right, is just the posterior GP that I'm using to make prediction of the distribution of my belief of the black box. And this internal stuff here is telling me how well under my predictions on average I'm doing, right, compared to the best I have seen so far. And now our goal is, of course, to find that variable x, right, which maximizes this. Because if I am able to maximize this, then under my current model, my current belief, on average, I will find a point which is better than the best I have seen so far. Now, to do this, to optimize with respect to x, right, you would need to do gradients with respect to x. There's a very nice set of papers how you would do that. But there's also very nice code on how you would do that. So given the Gaussian process prediction, all you can do, so this is examples from Botorch, which is another library to do Bayesian optimization. What you can do is you just can maximize this sort of an acquisition function and be able to find the new x to try. So here's an example of this, right, that is running on a function called the Levy function. So at the beginning, so the true function is this blue function. And as you see, I think it has its maximizer maybe somewhere here or so. And now this is the function which is the BO doesn't know, right? It's a black box for the BO. So and now we're running, this Gaussian process fit, right? Followed by the acquisition maximizer. And here I am showing you the Gaussian process fit and the acquisition optimizer. So what happens is that at the beginning, we have a high variance in this area from the Gaussian process because the points I have observed so far are this point, and that point. So I have no clue, what is going on in this area. And that's why the Gaussian process, when I fit it and I make predictions, it will give me a high variance on this area. And then what happens is that after I do this, I maximize my acquisition. And then my acquisition tells me, okay, go try a point here, right? And that's the acquisition step. So this is EI, it'll tell me, go try a point here. Now that's interesting because the model has said, okay, go try this point here, and we were very unsure, on what is actually going on, right? So we went and tried the point here. And then we refit the Gaussian process again. So after we refit the Gaussian process, what you notice, right, is that the variance here decreases, right, because we have seen some data point here, but we are still unsure what's happening here and kind of very unsure what's happening here. Now, why we are more sure here than here? Because we observed kind of like closer data points in a way. And now this expected improvement is saying, okay, you know what? I think I need another trial here to understand what's going on. And then it goes and tries. And then we fit the Gaussian process. And then we repeat this process again and again. After 4 steps, we have a fit that looks like this. And then if you keep repeating this until like 39 steps in this example, what you are able to see is that DBO acquisition steps actually start converging into the true global optimum of this black box function. So starting from a function with only 3 observations, and it doesn't know how the blue function looks like, this algorithm was able to, with the expected improvement, to do this over and over again, and after like 49 steps, to converge on this being the global optimum. Right. So this was with an expected improvement run. However, we have these other acquisitions I told you about, right? So now we can also try those other acquisitions. So now if we look at the other acquisition, one of them is the upper confidence bound, which I think is a very famous one, maybe the most famous one. What the UCB does, the UCB is going to trade off the mean, the posterior mean, right, and the posterior variance. And it's gonna take these two into account with respect to a parameter beta, and then maximize this instead of maximizing expected improvement. So with minor changes to the blowtorch code on the upper confidence bound, on the EI, sorry, you can actually just do the optimization of the upper confidence bound. And here I run the UCB again, and then I can show you the similar result that after some iterations, it started also with the same style as the EI, but after some iterations, it was able to recover the global optimum of this black box function. Okay. Now, all those that I have talked about, there are many libraries, there are many algorithms out there. However, I think the one of the libraries that has the SOTA algorithm so far is called HIBO, which is a library from my team called Heteroscedastic Evolutionary Bayesian Optimization. It is open source, completely open source. Please feel free to use it. And if you like it and you think it's useful, please feel free to start it. The story of HIBO was in 2020. So we started with a NeurIPS competition. So there was a NeurIPS competition that was organized at the NeurIPS conference. And that competition was organized by Twitter, SIGOPT, NeurIPS, 4Paradigm, and many others. The competition was something like this. So the competition was, you have many machine learning algorithms like random forest, support vector machines, and so on. And they all have, kind of 3 parameters you would like to tune. And now the question was, can we, kind of in offline phase tune those parameters of these algorithms? For example, like what is the regularization value for lasso algorithm and so on. And then this had to be uploaded to an online test. And then at the end, there's a final winner based on some evaluation use cases. So we actually, this is a very nice paper. I would urge everybody to read it, which is Bayesian optimization is superior to random search, and we kind of won, the first place in this competition. So we also got a paper from that, and please have a look at it if you are actually interested. But then I don't want to go into all the details here, but what we notice is that the recipe that I described for you before about Bayesian optimization, especially those assumptions we made, like fitting a Gaussian process with a Gaussian likelihood and so on, were not too realistic for these types of problems. So we modified the Bayesian optimization loop in 2 ways. Rather than, like fitting a standard Gaussian process, we fit a warped Gaussian process. And rather than doing a one acquisition, we did a multi-objective acquisition. So in other words, we noticed that the probability of the data was highly non-Gaussian. And we noticed something very funny, that different acquisition functions can give you different results. They can give you conflicting results. So here's an example of some data sets. It is really funny, for example, if you look at the MLP Adam Boston, you would notice that a UCB acquisition thinks this tolerance value, one of the hyperparameters we optimize, is actually great, But for a expected improvement, it's one of the worst ones, right? So if you run different acquisitions, you somehow get a different set of good points. So in order to solve this, we did a lot of warping of the data in order to deal with that. But maybe more interestingly, we used a multi-objective acquisition solver. That multi-objective acquisition solver was looking into a Pareto front between the three different acquisition functions I talked about: expected improvement, probability of improvement, and UCB. And this way now, we can kind of get rid of the conflicts between which acquisition is better than which other acquisition. And to solve this, we use an evolutionary method because it's a multi-objective optimization problem, which was NSGA2 back then. Yeah, and that got us the best paper, the winning result here. What is interesting is that our method, which is in blue here, is actually capable of outperforming many other methods. That's why I call it SOTA, including HyperOpt, Turbo, SKOpt, OptTuner, Navigrad, BOHB, and many others. The library itself is nicely implemented according to this two-step process I talked about, where one, you fit a Bayesian model, and two, you maximize an acquisition. So you would need just to define your design space, what your variables X are. But then you can nicely fit a Bayesian model, which is a GP, and then you can nicely maximize a acquisition step. So here's an example, of different ways like BO.suggest and BO.observe, which are different ways, to just suggest a point by fitting a Gaussian process, maximizing acquisition. And observe is like you evaluate the black box function. And with this small, change of code, you can actually go from BO into HIBO, right? So BO is the standard way. HIBO is kind of our algorithm, which I described. And you can nicely go from here to here by just a simple change of the code. You can also change the model, what type of GP model you want to use. And you also can change how many samples you want to evaluate in parallel. So this is like a batched version of HIBO, standard HIBO and standard BO, and then we can see we are better. But everything is nicely written and documented on this library. So GitHub, Huawei Nova/HIBO. Please be sure to leave us a star for us to continue to contribute to open source if you find this actually useful. Right. And here I just show some documentation on sklearn kind of estimators. Now, this BO as is, we have applied it widely to those problems I talked about in the first lecture. So the first one was this NeurIPS 2020 award, that I talked about, where we won this competition. Here we have a stable implementation of Gaussian process tricks. We have parallelization, and we have a multi-objective solver. And as I discussed, we had the SOTA results. We also applied this to the antibody design problem, where we actually looked into designing CDRs, right? And here are some of the results. So what you see in this figure is different sets of antigens. So 1ADQA is an antigen, 1FBIX is another antigen, and so on. And then you see different horizontal lines on each of those figures. Each of those horizontal lines are different binding levels of how good the binder you created, the CDR sequence you find, with respect to the specific antigen. And we do a lot of comparisons, right? So we do comparisons with genetic algorithms, we do comparisons with random search, with turbo, and so on. Now, what you can actually, what you can actually see is that our method, which we called AntBO SSK, special type of kernel, is actually capable of getting into a low binding energy, i.e. good binder, in a small amount of trials. So on 85 steps on average, we are able to get good binders. And then we also applied this to the chip design problem I told you about, this logic synthesis. And here's a competition we also won, I think in 2020, or 2021 from EPFL that deals with this. And the method is called Boyle's, right? So Bayesian optimization for logic synthesis. And then you can see that it's better than other algorithms. It gets 2.8 times reduction with respect to genetic and evolutionary algorithms. But most importantly, it gets 5 times sample complexity reduction to reinforcement learning. So not every problem you see in the world, you just throw at it reinforcement learning. There are problems better suited for other things. And then finally, as I said, the library is open source. Please feel free to use it and contribute to it, leave issues if there are problems there, and also please star it if you find it useful. Right. So with that, I will end the second part of the lecture, where we have described BO, and we described Gaussian processes, and we described acquisition function maximization. However, are we done? No, we're not. BO as is still suffers from many issues that we are still trying to resolve. One of them is what I call tabula rasa learning, which I will describe in the next lecture. And that is that every time BO has to start from scratch, we need to resolve that. And the second one is high dimensions, which we might talk on maybe in later lectures, or and similarly for the scalable and modular software. So with this, I would like to end this part of the lecture. And then I will be talking in the next lecture about meta-Bayesian optimization, end-to-end meta-Bayesian optimization to resolve the tabula rasa problem. So stay tuned for the third part, and thank you so much. Hope you found this useful.